Assalamu alaikum. Bismillahir-Rahmanir-Rahim. I welcome you to the 21st lecture for the series of lectures on advanced computer architecture. Today, after giving you a brief review of what we discussed last time, I will focus on the static scheduling for the multiple instruction issues in case of very long instruction word processors. Then we will compare the performance of different architectures, and we will discuss some algorithms to enhance the instruction level parallelism and improve the overall performance of multiple issue cases. Last time, we started our discussion on the static scheduling to exploit the instruction level parallelism in the pipelined data path. Here, we discussed that the compiler introduces stalls to avoid data and control hazards. However, we noticed that when we increase the number of stalls, the overall performance of the pipeline architecture degrades. Therefore, in order to overcome this problem, the methods of static scheduling were discussed. Furthermore, we observed that in case of loops, the loops are unrolled to enhance the overall instruction level parallelism. However, we observed that increasing the number of stalls, the overall performance is degraded. So we noticed that the compiler scheduling of the instructions is used in order to avoid the hazards and eliminate stalls. Furthermore, we observed that in case of loops, the loops are unrolled to enhance the performance and reduce the stalls. The number of stalls are further reduced when unrolled loop is scheduled by repeating each instruction for the number of iterations by using additional registers. And finally, we discussed that the impact of static branch prediction on the performance in scheduled and unrolled loops is used to enhance the overall performance of the system. We also observed that in superscalar processors with multiple issues, the static branch prediction results in decrease in the misprediction rate and therefore enhances the overall performance. Here, the misprediction rate is reduced in the range of 4% to 15%. Today, we will continue with our discussion of the static scheduling for very long instruction word processor, where the multiple issue case is dominant, and we have to take into consideration the impact of static scheduling for VLIW processors. So before I go into the details of the static scheduling in VLIW processor, First of all, let us have a review of what we discussed regarding the format of very long instruction word format. Very long instruction word contains a fixed set of instructions where the number of instructions may range from 4 instructions up to 16 instructions. We also know that a very long instruction word format, either it has got one long instruction or there are fixed number of instructions in a packet, and these instructions are issued in parallel. Since there exists explicit parallelism among instructions in case of very long instruction word-based processors, these processors are also referred to as explicitly parallel instruction computers or computing, and it is denoted as EPIC. It can initiate multiple instructions in a cycle by putting operations in a wide template or a wide packet by the compiler. The packet may contain 64 to 128 bytes. Now, in order to discuss the performance in the case of very long instruction word processors, first of all, let us see what is the overhead in case of superscalar processors, and then we will see that how this overhead is reduced in case of very long instruction word processors. We have already observed that in case of superscalar processor, the overheads grow with the issue width. For example, for a 2-issue processor, the overheads are minimum, whereas for 4-issue processor, they increases to a manageable limit. But as the issue width increases, the overheads also increases. Whereas in case of very long instruction word format, the overhead does not grow with the issue width. Furthermore, the early very long instruction word machines were rigid in their instruction formats, and they were required recompilation for programs for different versions of the hardware. Now, with the passage of time, certain innovations have been made in the design of very long instruction word machines, and this has in fact eliminated the need of recompilation, and hence the result is that the overall performance of very long instruction word has been improved only by implementing static scheduling and without repeated recompilation. Here, the processor design is changed, and wider processors are used, which employ multiple number of independent functional units, and the compiler does most of the work in finding and scheduling instructions for parallel execution. Furthermore, the compiler schedules and packs multiple operations in one very long instruction word, and hardware simply issues the complete packet with multiple instructions which are given to it by the compiler. So this type of hardware level enhancement in fact simplifies the compilation process, and recompilation for number of times is avoided, and large number of instructions are issued. Thus, it increases the issue rate to a higher level. Now, in order to discuss the performance of a very long instruction word processor, let us consider an example very long instruction word processor which can perform maximum 5 operations in one cycle. Here in this example, we will assume that the operations included in one packet are: there is one integer operation, there may be 2 floating point operations, and 2 memory reference operations. Here we further assume that the instructions have a set of 16 bits to 24-bit field for each unit, with an instruction length ranging from 112 bits up to 168 bits. Furthermore, we also assume that to keep the functional units busy, there must be enough parallelism in the code so that the complete operation slot is filled. So now let us see how a loop is unrolled to execute using multiple issues with very long instruction word processors. Here in this example, we will see that if unrolling the loop generates straight line code, then local scheduling techniques are used, and these techniques are operating onto a single basic block. Whereas if parallelism is required across the branch, then complex global scheduling is required to uncover the parallelism. Therefore, in order to explain these concepts, we will reconsider our earlier example of MIPS code, to which we have been considering while considering the performance of superscalar and scheduling in case of superscalar. Here in this example, we have been assuming that we want to add a scalar into a vector, which can be expressed with the help of expression shown here, that is xi is equal to xi plus s, which means that to an element I, for the array x, a scalar is added into it and it replaces the original value at the index position I. For this, let us consider this complete program. Here you can see that the first 3 instructions, that is the load, add, and store, they are used to obtain the first element of the array. Then to this element, it adds a scalar quantity, and the result is stored at the position from which the original value was being obtained. And then this loop is repeated for a number of times, whereas the loop evaluation is performed with the help of the add unsigned instruction, and the conditional branch instruction performs the operation with the help of which we can either terminate the loop or we can repeat the loop. Here you can see that in order to execute this code using multiple issue, very long instruction word, we may have to unroll the loop as many number of times as necessary to eliminate any stalls, ignoring the branch delay if there exists any. In order to explain this example, we will make some assumptions. these assumptions are that the compiler can generate long straight line code using local scheduling to build up very long instruction word packet. The very long instruction word processor has sufficient number of registers and functional units to issue up to 5 instructions in one cycle. That is, it has got 15 registers versus the 6 registers as we discussed in the case of superscalar processors last time. The loop is unrolled in order to make 7 copies of the body, which eliminates all stalls and it avoids any type of delay, which we observed in the case of superscalar processor, while talking about the same example over there. The unrolled version of the program is shown over here in this diagram, where you can see that it requires only 9 clocks to issue all the instructions. However, this table shows the very long instruction word instructions that occupy the copies of the loop instructions in unrolled sequence. Furthermore, here we assume that the register R1 has been initialized to a number 48 for 7 iterations. We know this thing that each memory location is 8 bytes apart. Therefore, starting the first value at number 48, the 7th value will be found at location 0. Here, the loop has been unrolled for 7 iterations to completely empty issue cycles. Thus, it eliminates all stalls. Here, each instruction comprises 2 memory reference operations, which is the load operation and the store operation. It also employs 2 floating point operations, that is the add instructions, and 1 integer operation, which may be the subtract immediate instruction. The multiple issues per cycle are depicted here in this table, which shows the type of operations in each instruction. Here you can see that in this example, the very long instruction word processor can handle 2 operations. Therefore, 2 load operations which do not have any dependence corresponding to the first and the second iteration have been issued in the first clock cycle. And the 2 load instructions for the third and the fourth iteration having no dependence are issued in the second clock cycle. Similarly, our very long instruction word processor can handle 2 floating point operations. Therefore, 2 add operations of the first and second iterations having dependence on the load instruction of the respective 2 iterations, and the load instruction that has a latency of 2 cycles. Therefore, 2 add instructions of the first and second iteration are scheduled in the third cycle to eliminate stalls. This is shown here with the help of arrows shown in yellow color. Similarly, as the floating point add and following store of the same iteration have latency of 3, therefore the store operation of the first and second iteration are scheduled in the 6th cycle. Moreover, the branch evaluation operation, that is the subtract immediate R1, R1, 48, and the branch instruction, that is branch if not equal 0, for the loop purposes have latency of 1 cycle when branch delay slot is ignored. Therefore, these two operations are performed in the 8th and 9th cycles respectively. Now, let us analyze the performance in case of unrolling and scheduling the instructions for very long instruction word processors. While discussing the performance analysis, we will look into this particular step based on issue rate and number of other factors. First of all, let us consider it from the point of view of issue rate. Here you can see that in this example, all the 23 instructions for 7 iterations have been issued in 9 cycles. As you can note from here that for 7 iterations, 3 executable operations like the load, add, and store, they have been issued for 7 times, which results in 21 instructions. Then at the end of 7th iteration, the loop evaluation instruction is there, and then there is a branch instruction. Hence, all these 21 plus 2 condition evaluation and branch instruction resulting in 23 instructions which have been issued in 9 clock cycles. This results in the average issue rate of 23 divided by 9, which is approximately equal to 2.5. As you have already solved the same example for superscalar processor, wherein the issue rate was found to be equal to 3.5. Therefore, it shows that there is performance enhancement based on issue rate in case of very long instruction word format when it is unrolled and scheduled by the compiler. Similarly, we can also look into the processor efficiency, which is based on the available slots. Here you can see that each very long instruction word in this example, it may have up to 5 operations. Thus, in 9 clock cycles, 45 slots are available. Therefore, the efficiency of very long instruction word processor, which is defined as the percentage of available slots containing an operation, is in this particular case 23 divided by 45, which is equal to 0.51, or efficiency is 51%. Similarly, we can also look into the performance based on speed of operation. The example very long instruction word code runs in 9 cycles, which results in 9 divided by 7 iterations, which is 1.29 cycles per iterations. This result shows that the very long instruction word processor is twice as fast as superscalar processor, when it is scheduled by the compiler. Now, with this much discussion onto the very long instruction word processor and its performance, let us have a discussion onto some advanced compiler supports. Our discussion so far has been focused onto the study of basic compiler techniques to exploit instruction level parallelism. Here we studied how dependents prevent a loop from being executed in parallel. That is how loop level parallelism is being limited. Whereas if we have to further look into the performance enhancement, we have to distinguish between the loop level parallelism and instruction level parallelism. The loop level parallelism emphasizes more on determining the type of dependence among the operations in a loop across the iterations of the loop, whereas the instruction level parallelism emphasizes more on dependence among the instructions in a loop. So this is the major difference between instruction level parallelism and loop level parallelism. The dependence in case of loop level parallelism can be detected by using different techniques. In general, the loop level parallelism is analyzed at the source level, that is at the higher level, and it is detected at that stage. Whereas the instruction level parallelism is analyzed after the compilation, that is when the compiled code of the instructions has been generated. So at the loop level, there may exist data and name dependencies. The data dependency in this case is basically occurring when operand is written at some point and it is read at a later stage from the same location. Whereas the name dependency can also occur and it may be eliminated, usually by simply renaming the particular locations, as we discussed earlier when we talked about the renaming techniques. Therefore, at this stage, when we have to discuss the detection and enhancement of loop level parallelism, we will take into consideration the data dependency. While dealing with the loop level parallelism, we have to consider the data dependence that occurs in a particular situation when the data accessed in some later iteration depends upon the data value produced in the previous iteration. This type of dependence is referred to as the loop carried dependence, which is usually denoted as LCD, where LCD stands for the loop carried dependence. We will distinguish between the loop level parallelism and the loop carried dependence with the help of this example over here. Let us consider these two examples to distinguish between the loop level parallelism and loop carried dependence. In the first example, where we will be considering the same previous situation, that is adding a constant to a vector, and for this purpose you can see that we can consider this loop over here, which is a for loop, which is to be repeated for 1000 times to add a scalar into the array which has been stored at 1000 locations in a sequence. Here you can see that there are two dependencies which may occur. The First is there exists dependence between the two uses of the vector x with an index value I within the same iteration. So this is a loop level dependence, but not the loop carried dependence. Whereas the second dependency occur between the successive uses of the index value I in different iterations. So it results in loop carried dependence. Here you can look into this in such a way that there exists induction variable xi. Therefore, the dependence can be identified through the compiler analysis near the source level, and it can be eliminated easily by loop unrolling as we discussed earlier. However, this was the simple case, but let us consider a relatively complex case where we can see how the loop carried dependence prevent the instruction level parallelism. Now let us have a look onto this example over here where a for loop has got two statements. Let us assume that A, B, and C are distinct non-overlapping arrays, and there exist two dependencies between the statements of the loop. Here the statements S1 and S2 use the values computed by each statement in earlier iteration. That is, A at an index value of I plus 1 computed in the ith iteration and read in I plus first iteration, but is to be used in the same ith iteration. However, you can see that the second statement S2 uses the value A at I plus 1 computed by the first statement S1 in the same ith iteration. Here, the first dependence is loop carried because dependence of each statement S1 or S2 is on the earlier iteration of the same statement. Thus, if this were the only dependence, the successive iterations are in sequence. Whereas the second dependence is not loop carried and S2 depends on S1, which is within the same iteration. Thus, if this were the only dependence, the multiple iterations of the loop could be executed in parallel by unrolling. So, as long as each pair of the statement is in an iteration is kept in order. Now let us consider another example of loop in which loop carried dependence does not prevent parallelism. Here in this example also we have got two statements in a loop. However, the dependence of the first statement onto the second or second onto the first is different as compared to our previous example. Here you can see that in order to analyze this example, we have to find the dependence between S1 and S2, and we have also to find if this loop is having parallelism or not. And if it does not have parallelism, then we have to see how we can make it parallel. So for this purpose, we will be taking the following two steps. In step 1, noticing that firstly there exists loop carried dependence between S1 and S2 as S1 uses the value Bi assigned in the previous iteration by S2. Therefore, S1 depends on S2, but S2 does not depend on S1. As a second step to determine parallelism, note that a loop is said to be in parallel if it can be written without cycle independence. That is, one statement depends on the previous iteration of an earlier statement of the loop. For this purpose, you can have a look over here in this example where you can see that loop does not have circular dependence. This is due to the reason that S2, that is the next statement, it does not have dependence on the previous iteration of the first statement S1. Hence, we can say that this loop can be reorganized by partial ordering to expose the loop level parallelism. However, in order to obtain this reorganization, we have to take two observations into consideration. The first observation is that the first iteration statement S1 depends on the value B1, that is the first value of B, which is computed prior to initializing the loop. And the second observation is that there is no dependence from S1 to S2. Therefore, there would be no cycle in the dependence and loop will be parallel. Therefore, in order to remove this dependence identified in the first observation, interchange the two statements such that execution of S2 is not effected. Considering these two observations, we can replace our example loop with the help of this code, which is shown over here. Here you can see that the S1 does not have dependence on S2. So the two statements are not loop carried. Hence, the iterations of the loop can be overlapped. In this particular case, what we have done is we have brought the computation of A1 and the 101st value of B out of the loop, and the loop is repeated for 99 times instead of for 100 times as in our first case. Because in our first statement S1, we have interchanged their positions, and that first statement S1 of the previous code, that has been now made as the statement S2 in this particular code. And similarly, the statement S2 has been made as the first statement in the loop. And by the time the second statement is issued, it has got the required values available. Therefore, it can be overlapped. So far, we have been talking about the impact of data dependence on the loop level parallelism. We also noticed that the loop carried dependence is crucial in this case and is removed to enhance the parallelism. Now we will discuss how compiler determines the dependence to enhance the parallelism. We know that finding of dependence in a program is important to have good scheduling of the code and also to determine which loop might contain parallelism, and finally to eliminate the name dependence. So let us first of all see how compiler finds dependence. The compiler detects the dependence using dependence analysis algorithm. This dependence analysis algorithm basically works on the assumption that array indices are affine and there exists a greatest common divisor of the two affine indices. Let us first of all see what do we mean by affine index. An array index is affine if it can be written in the form of an expression A multiplied by I plus B, where A and B are constants and I is the loop index variable. So you can see that in a loop, for example, for I is equal to 1 to 100, where we have to say, compute the value x of 2I plus 3 is equal to x of 2I whole multiplied by 5. In this expression, here the index value 2I plus 3 is affine because here the value of A is equal to 2 and the value of B is equal to 3. Similarly, in a multiple dimensional array, index is affine if index of each dimension is affine. So with this much definition of affine index, let us discuss the algorithm to find dependence. We know that there exists dependence between two references to the same array in a loop if two affine functions can have the same value for different indices between the bounds of the loop. For example, let us consider an array element stored with the index value AI plus B and loaded from the same array with the index value CI plus D, where I is the loop index variable that runs from M to N. Then in this particular case, we can say that the dependence occurs if the following two conditions hold. The first condition is that two iteration indices, say J and K, are both within the limits for loop, that is, J is ranging from M to M and K is also ranging from M to N. The second is that the loop stores into an array element indexed by A into J plus B, and later on it fetches from the same array element when it is indexed by C into K plus D. Then we can say that the dependence exists if the expression A into J plus B is equal to C into K plus D, which means that the two affine indexes are equal. Now, in order to find the dependence, we know that in reality, it is a very, very complex process. Therefore, we usually use the technique of greatest common divisor, that is GCD, which is a simple test to find out if dependence is absent. Now, the greatest common divisor test is one where if a loop carried dependence exists, then the greatest common divisor of the two affine constants of index, that is in our earlier example, that is of A and C, they must divide the difference value, that is D minus B. This you can see with the help of this example over here. In this example program, where the value of x, which is having an index value of 2 into I plus 3, here the value of a is equal to 2 and the value of b is equal to 3. And on the other side of the expression, where x having an index value of 2 is to I, here c is equal to 2 and d is equal to 0. So from this we can find out the greatest common divisor, which is a function of a and c. And in this example, the value of the greatest common divisor comes out to be equal to 2, which is in fact the greatest common divisor for a is equal to 2 and c is equal to 2. Similarly, the value of d minus b in this example is equal to minus 3. Here, as 2 does not divide by minus 3, therefore we can say that for this particular loop, no dependence is possible. So as a conclusion, we can say that the greatest common divisor test is sufficient to guarantee that no dependence exists. Now, but this much discussion on to the instruction level parallelism versus loop level parallelism and loop carrier dependence. Today we will conclude our discussion, where you can note that today we have introduced the concept of determining the loop level and loop carrier dependence. We noticed that in most of the cases, loop carrier dependence prevent parallelism, and then we have to use certain techniques in order to remove the loop carrier dependence. So with this much discussion, I'll say you Allah Hafiz today till next time, where we will discuss the next further topics for the static scheduling. Thank you and Allah Hafiz.